All right. Good morning, everyone. I hope you enjoyed the party last night, have slept well, and had a good breakfast. Thanks for coming to my talk, Image Processing with Halide. My name is Svenn-Arne Dragly, and I work in a company called Zivid, located here in Norway, in Oslo. So when I was a student, I studied physics. And as many other physicists and mathematicians, I grew a strong affection for elegant equations, or equations you might even call beautiful. You know, these things that mathematicians and physicists are all on about because they're not necessarily simple, but they're often compact. They encompass a lot of information in very little text or symbols. And like these equations, which are Maxwell's equations, they can explain a lot of phenomena in the world. So Maxwell's equations are the ones including, or in addition to the Lorentz law, that can explain basically everything that has to do with classical electrodynamics. And that's super powerful and, in a sense, beautiful in the eyes of physicists and mathematicians. Now, as I was continuing my studies, I moved into computational physics, and I grew an affection for programming, and over time also for pure functions, which is maybe an affection I share with others in the room here today. I know there's a lot of interest in functional programming around. And these are, in the same way, beautiful because they can be reasoned about more easily. So a pure function is one that gives you the same output for the same input. It has no side effects. Many feel like if you use pure functions, you can make more maintainable code. It's also code that's easier to reason about for everyone who comes after you. And so many programmers have an affection for pure functional programming. But as I moved further into this study of computational physics, I learned that the real fun stuff is when you can do simulations and modeling on really large systems. But if you do that, then you need to optimize your code. And then suddenly you have to mix these nice equations or algorithms, and sometimes also the nice pure functions you had, in between all the optimizations that you're doing. So this example on the slide is just some random example, just to show that if you're wanting to compute an image G that is a function of f, you might want to intertwine the computations in the for loops so that f is computed when you're looping over y, and maybe that's efficient, maybe that gives you some cache locality, maybe that enables some compiler optimization that just happened to work on your machine. And the challenge here is that when you're doing these optimizations and you're moving the equations in between the different for loops, maybe you add some vectorization and so on, in the end, you end up with something that's really hard to read and maintain, both for others and for you. It starts to get hard to see these equations that you started with and make sure that when you're doing these optimizations, you're not messing with the actual algorithm that you're trying to implement. So this is where Halide comes in. Halide is a language and library that allows you to decouple the algorithms from the optimizations. So here's the same algorithm in a sense that as was on the previous slide. So we define f of y to be the square of y. We define g of x and y is like a 2D image, and it's a function of the y that we had from before. But we haven't said anything about how we want to compute this. We're just saying something about the relation between the two functions, f and g. And Halide then enables you or gives you a lot of tools to say something about how you want to optimize this. How do you want to interleave the computations of the different functions? So I'll get back to this and we'll go into more detail, but this is just an example of how I can say that I want f to be computed at the same loop level as g is computed for the loop variable y. And finally, Halide further postpones the actual execution and calculation. So you can define your algorithms, your optimizations, and then you can perform the actual realization or execution of your algorithm. And there's also another option that we'll get back to, which is to defer the execution even further, not run it in the program where you define all of this, but rather compile it down to a binary file that can be linked to your executable. And by the way, I think it's important to give credit where credit is due. We are not the creators of Halide. We are just using it. So just to avoid any confusion, I wanted to point out that Halide is made by a great team of core developers, and it's an open source project with a great community. Even the core developers who have been working on this for 10, 12 years are very responsive and very active. And I'm very grateful for how nice that community is and how nice it is to work with the people who are creating Halide. But we are not the ones making it. We are making these things. So I work for a company called Zivid, and we make 3D cameras for robots. Or as I'd like to say when I'm in a family dinner, I make robot eyes. And the reason I say that is because it's kind of true, because most of the robots in the world today, they are blind. So they have to perform essentially not just the same task over and over, but also the same motion over and over, because they're not able to react to their environment because they can't see it. So that's where we come in. We can put our cameras on, or we can sell our cameras to customers who put them on the robot arm or next to the robot arm, and then they're able to see the environment that the robot is working in. And this unlocks the potential of robots to do more work in, for instance, logistics, in automation, manufacturing, and to perform tasks that today have to be done by humans, even though they might be dull, tedious, and sometimes even dangerous to do. So what you get out of our cameras are these point clouds. We strive to give very high precision and high detail point clouds in a very short time. Almost always below a second, and sometimes we have requirements to provide point clouds below tenths of seconds. So we talk a lot about how we want to get these robots to do work that humans have to do today. And to achieve that, we like to say that we need human-like vision for our cameras. And the human visual system is very complex, and we're not going to replicate all of it, but we've tried to kind of look at the most essential parts and figure out, okay, what is it that the human eyes and the human visual system can do that we need to do? And the simple conclusion, if you want to get depth information, is to see that we have two eyes, like many other animals. And that is the first step in many cases to get depth perception, because the way you can see depth, both as a human or in a stereo camera system, is that you look for the same feature in the two images that hit the two cameras or the two eyes. So as in this case, we're looking, for instance, for the eye, and we look for it in the two cameras. And as soon as we have that feature in both images, we can trace a ray from the origin of each camera in through the image and the pixel where we saw the feature we're interested in, and into the 3D world. And where the rays intersect is where that feature is in space, or I should say, where the two rays are closest, because it's pretty hard to get two rays in 3D space to actually intersect. So this is how a lot of stereo camera systems work. Find the features, you find the points, and then if you do this for a lot of points, you can reconstruct what we call a point cloud for the surface of the object in front of you. Now, yes? Question. Yes, there are stereo cameras that have standard interfaces as well. Yeah, so the question is whether there are common interfaces for different cameras when you need to feed this information to robots. And yes, there are some common interfaces, and some providers like us provide both adapters to those interfaces and their own APIs. So I guess it depends on which camera you're using. But there's one problem with stereo vision, and that is that there's a lot of things in the world that have very few features, and especially in industry, where you might want to pick boxes, and the box basically just has a flat surface, so everything looks almost the same. So when you're using a stereo camera system, you need something on top, kind of like how the human visual system works, and you deduce more information to try to kind of extract a feature from this featureless surface. And that turns out to be really hard. So we use a trick instead, and we essentially replace one of the cameras with a projector. Because then we can shine light onto the object and create our own features. And as long as we know which ray we shine light along, we can now do an intersection with the ray of the light we're shining with the ray of the light that we're seeing, and voila, we get a point in space. But doing this for like one point at a time is going to take way too much time, because then you would essentially need the number of images as there are number of pixels on your camera, which would be 2 million images easily. So what we do instead is that we use patterns. We use a handful of images with carefully chosen patterns, and that's enough to give us the information we need to get precise depth. And as you might notice in this little simulation with the monkey head and the two boxes, I'm showing only vertical patterns here. And there's a reason for that. Because it turns out that if you use horizontal patterns, since you already have a horizontal offset between the camera and the projector, there's something called the epipolar geometry that I'm not going to go into detail about, but we essentially already have the information about where horizontally on the projector we're going to be when we know where we are on the camera. And this is actually seen intuitively if you look at this video, that a horizontal pattern gives no distortion, like there's nothing that changes as we move the object back and forth in the patterns that we see. While if we have vertical patterns, if you look closely, you can see that the patterns are kind of shifting left and right depending on whether the object is closer and further away from the camera. So this is a very shorthand way of saying that the most information is in the vertical part of the pattern, so let's just use that. And another way to think about it is that you could shine a line vertically and just swipe that across and look at the intersection between the plane that that line kind of makes through space and the ray from the camera. And that gives you essentially the same information. So I said in the description of this talk that we would talk about the journey that we had. So not just about what we're doing, but also about how we switched from the OpenCL framework to Halide. So first of all, I want to say something about why we wanted to move away from OpenCL. And one of the main reasons was that we saw a pretty big gap between the R&D work that was being done in MATLAB and Python, and then the production work that was done by other people in OpenCL. So we would always have this R&D work that needed the translation phase over into OpenCL. We wanted to shorten that down somehow, if possible. We also wanted to reduce the amount of hand-optimized code we had to write, because that's always tedious and, as I mentioned, error-prone and harder to maintain. And we kind of, what actually triggered looking for alternatives was that we saw issues with certain OpenCL drivers for even major vendors, especially when using more advanced and modern features. So we had the choice either to stick with kind of the lowest version of OpenCL that was running on all our customers' GPUs, or not run on those GPUs at all and use the more advanced features. And over time, we realized that there were too many GPUs out there that we couldn't run on when we were using the features we wanted to use. So we got this nudge to essentially look for alternatives. So what is Halide? Halide is a domain-specific language that can be used for computations on images or tensors, as they like to say. I just think of them as n-dimensional buffers. And it's implemented in C++, but it's embedded in C++ and Python. So even though it's a language of its own, it's a domain-specific language that is, for all intents and purposes, working as a library when you use it in C++ and Python. So it's not a whole new language. It's just a language that uses the building blocks of C++ or Python. It helps optimize dense numerical kernels, such as are used in image processing, in computer vision, and machine learning. And as I mentioned, it is a tool to decouple these algorithms from the optimizations that you want to do. So why did we choose to move to Halide and not just some other framework? One big reason is that Halide compiles down to a number of architectures and platforms. And I highlighted OpenCL here because that was actually a benefit for us to choose something where we could still compile to OpenCL and know that we would at least run on the same platforms as we were running on today, but have the option to then compile to other platforms as we move forward. Like for instance, to run on a Jetson, you need to use something else than OpenCL, and knowing that we could easily switch to CUDA, that was a huge pro in our thinking. I'm not going to list all the other platforms, I'm just putting them up there so that you can look for your favorite one if you're interested. As I mentioned, Halide also is open source and has a very welcoming community. And what struck us was that we hadn't really heard about Halide before, but it turned out to be used in very large commercial projects. And that's because some of the creators are working in Adobe, or have been working at least, in Adobe, in Google. Some of them are now in Facebook. So it's used in Adobe Photoshop, in the Google Pixel camera, and in YouTube when YouTube does some of its video processing. So kind of seeing that track record, we felt more confident that, okay, this might actually be a kind of mature library and not something that's just a research project and where we will have to find all the bugs ourselves and then live with them as we go. Now, it turns out that there are some bugs that were still in there, but that's how it is. It's a very mature library, I would say. Okay, so I'd like to give you a little introduction into how to write a Halide program. So the building blocks in Halide are the vars and the funcs. Those are kind of the main building blocks. So a var is an image coordinate or a buffer coordinate if it's in multiple dimensions. And it's just a placeholder. You're not saying what number x and y are just yet. That's kind of just to have some name to put into your equations. The funcs are these mappings from the image coordinates to the values. So when I say f of y equals y squared, that's just an early declaration of what f of y is going to mean, and then it's going to be evaluated later. So it's kind of like lazy. Excuse me. It's also a pure function, these funcs in Halide. So they will have no side effects. You can't access the network or anything in here. It's just a pure functional mapping from the image coordinates to its values. And then, as mentioned, Halide allows you to declare how you want to perform these optimizations. So again, f compute at gy means please put the computation of f inside the same loop as you're going to compute g when you're looping over y. And that is equivalent to the code you see on the bottom there, depending on what else you will say later about where you want to compute g, of course. But yeah, in essence, if g is computed like this, then f is going to be in the loop over y, instead of, for instance, being computed every time you loop over x. And then finally, you can tell Halide that, okay, I've made my decisions, I made my optimizations, now please execute this function and show me or give me the result. And that's going to give you a Halide buffer back. But since we're working in Python here, that's that's a buffer that supports the Python buffer protocol. So you can also then just throw it into matplotlib, which is something that's super powerful for us, because when we were working in OpenCL, the tooling around OpenCL and working with the buffers that we get out there is not obvious, at least. Like, we could always write it to an image, or we could write our own image viewer, but being able to work with the tools that researchers already are familiar with, like even if you're coming from MATLAB, using Matplotlib is pretty much straightforward. That was a game changer for us. Or, as mentioned, you could also compile then to binary files and link it into your executable, which is what we're doing for our production software. And just to have it mentioned, since I know a lot of people in the audience here are C++ fans, Halide can be used in C++. That's maybe also the most common way to use Halide. And the difference is minimal. It's essentially just how many times you have to say const auto or auto and put a semicolon at the end of the line. But I'm choosing to use Python in the slides only because we are using it ourselves, so it was easier to find the examples, and because it's a bit more compact, and I would say a bit more readable as a slide format. Okay, so in the rest of this talk, I want to use this driving example, referring back to what we talked about earlier on how we use these vertical patterns to find where on the projector the light is coming from, and being able to use that information to do the intersection between the plane of the projector or the column on the projector and the line from the camera. Now, we're not going to do the actual reconstruction and intersection part. We're only going to stop at figuring out in the camera space where on the projector did the light come from, or from which column on the projector did the light come from, which is what's shown in the image here. Yeah, so as mentioned, same as we talked about before, it's this intersection with the plane that we're looking for, or we're gonna set us up to compute. The input images look like this. Again, vertical patterns. And the concept here is pretty simple. We divide the scene into areas that have light coming from the projector, either on or off. And we, in the different images, slice this light into more and more pieces. So in the first image, we're lighting half the projector. In the second image, we're still lighting half the projector, but doing it in like an on-off fashion, and then using more and more slices as we go. And for those of you who have been doing a lot of computing with binary numbers, you might notice that this is essentially encoding information with light about where on the projector the light is coming from as a binary code. It's on or off, which means that we can turn it into a decimal number afterwards. So to explain this in more detail, if we take one of the pixels in the image, just chosen randomly here, we can see the light intensity on the y-axis and the image index on the x-axis. And as you can see, the light will be on or off with some noise. Especially in the real world, there will be a lot of noise in these images. So the algorithm that we're going to implement works as follows. We find the minimum value across all the images. We find the maximum value, and then we set a threshold as the average of the minimum and maximum. That's how we figure out whether something is on or off, because the values themselves are floating point, like it's a light intensity, so they're not on or off yet. We need to set this threshold to be able to figure out, okay, where is it on, where is it off? And that's how we set this. And then once we've done that, we can just look at, is it above the line, or above the threshold, or below the threshold? That gives us this binary code, in this case 011010 over the images. And then we can turn that into a decimal number, and that will give us where like a number for which column on the projector the light came from with some resolution. So in Halide, when you're setting up your algorithms, you can provide params that are also supposed to be fed into Halide later. And those params can be images. So in this case, for the input images, we are going to use the image param, and we will tell it that it has a type. In our case, we use 16-bit 16-bit images. We say that it's 3 dimensions because it's images, which are 2-dimensional, and then there's a stack of them. So that gives the 3rd dimension to the input images. And we give it a name. And the name here is optional. You can skip it, but I guess Halide noticed that there was no way to actually find the variable names when you're working in C++ and Python of the object that you are yourself. So it's a way to give that information to Halide so that when you're doing debugging, tracing, profiling later, you will actually get reasonable names out. If you don't, then everything is going to be called like F1, F2, F3. So this is just for debugging purposes. Then in the next slides, we'll define the algorithm that I just talked about. And after defining that, we can decide to load our images whichever way we want. In Zivid, we read them from the camera. If you're working in Python, you can just load some PNGs from file and put them into a NumPy array and then pass that on to a Halide buffer. And then if you want to realize the function or the algorithm right now, you can set those images on the image param, and then you can realize and look at the result. Or you can skip setting the images right now, compile to a binary file, and then you will get a function that accepts the image param as a buffer that you can provide later. Again, that's how we're doing it in our production code. So let's compute the maximum value in each pixel. Again, we define these vars, the image coordinates, x and y. In this case, I know we're just going to work with 6 images, so I'm just going to make that a static value at 6. And then I need to define a reduction domain because we want to calculate the maximum value. And there's no way to write code in Halide with like raw for loops. The whole intention of Halide is to figure out the nesting and order of all your for loops later. But you have to tell Halide somehow that there's going to be a reduction here. And that's done by saying that I want a reduction domain over the number of images. So it's a reduction domain, in this case 1-dimensional. It's going from 0 to the number of images. That's the range. Then we define our maximum function. And now we first give it the initial function definition. And this is a very roundabout way of saying that we initialize it to 0, but I'm putting it with the min value of a uint16 here just to show that that's good practice if you later decide to change the type so that you actually get the minimum value of int16 if you should change to that later. But that's the initial value here. We set the maximum to 0 first, and then we compute the maximum value by using the max function and giving it the previous maximum value and the input images, where the last index here is this reduction domain. And that's how you tell Halide that I want you to perform a reduction on this for the computation. And if you prefer to read procedural code instead, then this is the equivalent. We would loop over all the coordinates, initialize the maximum value to 0, and then calculate the maximum value of the previous one and the input image for all the images in a for loop. And this is essentially the code that Halide will generate for us as well. That's done, yeah. And for the minimum image, it's just the same. Just swap the minimum and maximum. So I'm gonna skip over that easily, but it's just the same as we did in the last slide. For the threshold, it's pretty straightforward. We say that the threshold in the XY coordinate is going to be the maximum value in the same coordinate plus the minimum value divided by 2. That's how you get the average. And then finally, we can see if each image is above the threshold. And that is done by defining this binary code func. And this is now, again, a three-dimensional one where we have this I var, which gives us the image index and tells us the binary code for that image. And now you can see we have gone from the input images that had floating point values essentially to, or not floating point values, but real life values, not just Boolean values, to these images that now have a binary code where yellow is on and purple means off. And then finally, we can get the projector column. We get our decimal code with a similar reduction domain. We initialize it to 0, but this time we add to it the binary code times 2 to the image index. And I'm sorry that it's the image index reversed. That was just to get the projector columns the right way, which was left to right. But yeah, it's the binary code times 2 to the power of the image index, which many of you will recognize as just a regular conversion from binary to decimal. And then finally, the projector column is typically normalized, so we're going to do that here as well. We take the decimal code and divide by the largest number we can get, and then we get this nice image of the projector columns. We're done. The algorithm is finished, and it's probably going to be pretty slow. And yes, it is. Well, at least for our standards. This will take 61 milliseconds to compute out of the box for this simple step in the very beginning of our pipeline. And that's taking way too much of the precious time that we have. So we're going to speed things up. But first, let's talk about what actually happens now. Because now we haven't told Halide to schedule this or optimize it in any particular way. We're just saying in our little schedule function, just pass. I don't care. Just use the default. And Halide will then give you what's called an inline schedule. So it will try to inline every computation that depends, or any func that another func depends on is getting inlined in the func that uses it. And that means that essentially, if everything was just straightforward funcs using funcs, then everything would be inlined. But since we have some reduction domains, there are some things that actually need to be computed before they're used. And that's why you end up with what you're looking at on the right-hand side here, the so-called loop nest that you can tell Halide to print for you. And as you can see here, we get a loop over the image coordinates as expected. And Halide will start to initialize the decimal code to 0. And then it will make a loop over all the images to compute the decimal code. And now the problematic part starts, or may be problematic depending on your architecture. Halide will then, since it's trying to inline everything, wait with computing the minimum value until it's needed by the decimal value, which is then going to be inside the loop over all the images, which means that it's going to add another loop over all the images inside the loop over all the images, which could be a bad idea. And in this case, it turns out to be, at least on my machine. In other cases, doing additional work can actually be better than reducing the number of reads. So it depends. This default schedule in Halide is actually a very reasonable one. Because often inlining is good, and also it's the one that uses the least memory because it doesn't retain anything. It just computes everything as needed. And then similarly, for the maximum image, we compute that by looping over all the images. And then we have all we need to compute the decimal code. And we go out of that loop again, and we can compute the projector column, which was just the decimal code divided by the largest value. Voila, that's our current pipeline, and I'm going to call this the baseline at 61.2 milliseconds. We can thankfully also ask Halide to, or use a tool that Halide provides to visualize what this looks like. So the blue dots here are the reads. This is, by the way, scaled down, so it's not the full image, as you might see as it progresses. It's a scaled down version of the images, just to make it easier to look at. But as you can see, it reads with the blue dots from the input images. The yellow dots are writes, so it will read from the input images, write to the minimum and maximum value, and then also write to the binary code, which, as I said, was, or maybe I forgot to mention it, but it was inlined in the previous slide, but I forced the visualization here just to make it easier to look at. And then finally, the decimal code and the projector column. And it's a bit hard to see here, but the blue lights on the top or dots on the top are blinking actually really, really fast and many, many times. So I'm going to slow it down a little bit so you can see that there's a very large number of reads from the input images here. And that's most likely what's giving us the bad performance in this case. But scheduling inline is just one extreme in Halide, and I like jumping from one extreme to the other before we move on. So I'm going to show you the other extreme, which is to tell Halide to compute everything at root. So we just say for all the functions or funcs that we defined, compute root, all of you. And that is telling Halide that I want you to be done with this thing before you compute anything that depends on it. Just get this one out of the way, store it in memory, and then you can compute the next thing. So that in practice means we're going to get a for loop over x and y for the maximum value, but not just the maximum value, but also the initialization of the maximum value. So it's going to initialize the whole image zeros, and then it's going to make another loop over x and y and all the images to produce the maximum value. And similarly for the minimum value, and then it's going to loop over the entire threshold image, and so on. So this is another extreme, as I said. It's, in a sense, using the maximum amount of memory, almost. It's trying to retain everything before it's needed. And it's the extreme that doesn't do any of this, I think. It shouldn't do minimal recomputation of the same values, at least. Yeah, I'm going to skip these last ones, but you get the picture. If not, the animation is pretty good at showing this. So the maximum image is computed, the minimum image is initialized and then computed, and you can see that it's doing all the reads all over again over the input images. Then it's computing the threshold by using the input images again, and then the binary code, the decimal code, and finally the projector column. And again, each image at the time. And this is slightly faster, at least on my machine. We're down to 48 milliseconds. Some might call it an improvement and ship it. I don't think we're done yet. So the best thing to do in Halide is, of course, as with everything else, to strike a balance. And the best way to do that here is to use the functions compute at and compute with that I've already been mentioning a couple of times. So here we're getting into the details. We say that I want the minimum value to be calculated at the same loop level as the projector column when it's looping over the variable x. We're moving the minimum value back in there. And that moves both the initialization and the calculation into that loop level. However, I noticed that there's another thing we want to do, and that is that we want to be smart about computing the minimum and the maximum, because they don't have to do that in their own loops. They can do it in the same loop. Let's do that. We do that by saying maximum.update, which means in the update definition that you have, please compute with the update definition of the minimum, which is minimum.update, over the loop of the reduction domain, the RDOM. And now it's starting to look like the code I would have hoped to write, maybe, if I wrote the procedural version myself. And then we do the same for the threshold and the decimal code. Make sure that those are also computed in the same loop level as the projector column. And that looks like this. Essentially, the visualization looks a lot like when we use the inline schedule. It's just that the blue dots on the top, it's a bit hard to see, but trust me, they blink a lot less. So there's a lot fewer reads of the input images now. And that puts us on time used at 16 milliseconds and 3.8 times speed up of the algorithm, which is getting decent. Now we're talking. But of course, this is just running on one thread on my machine, not vectorized or anything. So this is where kind of the really nice superpowers of Halide are coming in my opinion. Because now we can introduce vectorization just as easily, and we can do it without messing with the algorithm. And we do that by splitting the loop over X into a loop over X outer, like chunks of X values, and then an inner X inside those chunks. So we define those vars. We then tell Halide to split X, and then it's as easy as just saying vectorize over the X inner. And I'm doing this on the projector column func because I have already told the other funcs to be computed at this func. And it turned out in this case that it was enough to just compute the maximum and minimum at, and the others would actually follow or get inlined. So that's what I've done here. And now we're down to 3.7 milliseconds and a 16 times speed up. And now the visualization is starting to look really cool because now you can see that it's actually doing these vectorized reads and operations on the values. So now we're starting to use more of the advanced features of my CPU. I'll just let this run for a little while. And I should mention that I've slowed down the visualization now because it was running a bit too fast, which is like everything was done. So that's why it looks like it's slower, but it's running faster when you're actually running the algorithm. Okay. And next, just as easy, we can ask Halide to introduce parallelism. So we got vectorization with almost a one-liner, at least 3-4 lines. And parallelism is actually a one-liner. I just say, I think you can compute this faster if you do it in parallel over the rows. And that turns out to be true. That puts us at 1.9 milliseconds and a 32x speed up. And the visualization looks insane. So now even the visualization is going pretty fast. And finally, the thing that we're actually doing in Zivid, since we want to run on the GPUs and use OpenCL or CUDA or other GPU frameworks, is that we can tell Halide to use a GPU tiling technique instead. So that requires us to split both X and Y into inner and outer variables, because then we can use the GPU tile function and say that we want X and Y to be split into X outer, Y outer, X inner, Y inner, and then give it a tile size. In this case, I found that 16 times 16 tiles was pretty optimal. And then, as you see on the right-hand side, Halide will now turn all of those outer for loops into what it's calling GPU blocks and GPU threads. And I'm not going to go into details about how that actually works, but I can show you the visualization on the next slide on how it conceptually works. But I should mention that Halide did not allow me to visualize how it's actually running on the GPU, probably because it doesn't actually know, because it's a bit up to the GPU drivers itself to decide exactly which order things are going to happen. But it will show you that things are happening in tiles. So the actual reads and writes are probably not happening the way they actually are happening on the GPU, because that's dependent. But the important part is that we're now at 0.6 milliseconds and 100x speed up, which is pretty nice considering that I have not changed the algorithm once along the way. I've only changed the optimization. So I know at least to our in our experience that we can trust Halide in that we get the same images as we did before, down to, of course, floating point precision. And I should mention, if you're interested in using Halide yourself, there are also auto-schedulers. I don't have any more slides on that in this talk, but what those are is essentially a way that you can write your algorithm and you can ask Halide to run one of its auto-schedulers, and those will try to find the optimal schedule for your algorithm on the current machine. And depending on which one you're using, they're either very simple to use, or you have to provide them some additional information, and they can try to find schedules on the CPU alone or even on the GPU. So yeah, you should check that out if you're interested in using Halide yourself. Right, so let's continue this journey. We started rewriting our OpenCL pipeline in Halide when we saw these benefits and saw that, hey, this might actually become very useful for us. And we had a honeymoon period where Halide fit really well, especially in the earlier parts of the image processing pipeline. And that's the parts where we're working only on images or n-dimensional buffers. And everything can be expressed as a feed-forward graph, just like the one we talked about now, where we have the input images, they are used to calculate minimum and maximum and the binary code, but everything is just feeding forward all along until we get the projector column. If you don't have that, then suddenly Halide is not the right fit. And especially dynamic programming algorithms, think like Dijkstra or A-star, those are not the algorithms you want to run in Halide, even though you want to have all the vectorization and parallelism and running it on the GPU. And that's just because it doesn't fit into the paradigm of Halide. And unfortunately, we got burnt by this pretty far into the project because we had one of our filters which was using a dynamic programming technique, and yeah, that just didn't fit, even though we tried really hard for a long time. And that's where I recommend people like myself to sometimes just look outside the box and not try so hard to get the square peg into the round hole. And there's also you can do some recursion in Halide, like the reduction domains allow you to have recursion on the same function essentially, but you can't have anything that feeds back into the graph. So yeah, advanced recursive algorithms also don't fit that well. But Halide thankfully has a way to kind of bail out if you need to. Of course, you can run code on the side of Halide. You don't have to put everything inside Halide. But if your pipeline, like ours, is looking all green and shiny, it's like all the pieces fit together, and then bam, there's this dynamic programming part that just doesn't fit, then thankfully you can call an extern function from Halide. And this is kind of like just declaring in a header that, hey, there's this function, I know I can call it, here's the signature, and the linker will take care of it when we get there. So if you saw Anders's talk yesterday on symbols, this is just one of those undefined symbols. So this doesn't work when you're using Halide with just-in-time compilation and want to realize your results like in the same code as you're developing them, but it works very well with the ahead-of-time compilation. So when you compile this down to object code or an object file and you link it to your executable later, as long as you provide the function that you're referring to with the correct signature, then the linker will find it and Halide will call it for you. And what's nice about this is that even though we use it at kind of the top level, we have like one big buffer is computed, and then we have one of these compute root functions that we want to run on the entire buffer. If you're not using OpenCL or the GPU, if you're using the parallelism and vectorization features in Halide instead, you can actually get Halide to call this with chunks of your buffer. Or I think technically it will give you the entire buffer, but it will also tell you the coordinates. and where in that buffer you should do your computations and do all of the parallelization and things that are needed on top. But then you really have to take care of that you're not doing anything that could cause a race condition in your function. So it gets more advanced. So yeah, the caveat here is that you cannot call any custom OpenCL functions, for instance. So you can't inject an external OpenCL function in the GPU code. Unfortunately, because that's what we really wish we had, but that's how it is. So in the end, we rewrote at least almost our OpenCL code in Halide, and we were pretty happy about that. We think that we have gotten a lot of benefits from using Halide, both to separate the algorithms from the optimizations, but especially being able to do the R&D work in the same environment as the production code lives. And we are continuously trying to add new tools internally to use Halide better. We have, for instance, figured out that you can use matplotlib to add some nice sliders and now play around with the algorithms that are running live in Halide and just find the parameters you need in the production version of the code, which is way faster than what we did before, where we would have to compile the entire SDK and then start playing around with the parameters, compile again. So yeah, just working in this interactive environment with the right tooling, that's great. But even though we're very happy about choosing Python and using Python with Halide, we have to admit that we are missing the static type checking that you would get if you use the C++ version. So we have had our occasions of putting what we thought was a 32-bit integer into a function, but it turned out to be 8-bit and it was doing all kinds of overflows and the images just looked like garbage and nobody understood why, where the C++ version would have told us this right away. So yeah, we're trying to retroactively add some typing information into our code in Python now, which is of course possible, but yeah, Halide doesn't come with full typing for the Python bindings yet. So that's it from my side. Thank you all for coming. And if you have any questions, I'm happy to answer them. Questions? Why are you regular pattern? Very good question. So there are definitely the 3D cameras that do exactly that, and that's doable. And it comes down to which problems you want to solve and to which degree you can get the precision out when you try to solve those problems. So yes, you can have a 2D pattern with 2 cameras, look for the same features, and I think is it the Kinect that essentially works like that with just one camera and a 2D pattern, and that gives more speed essentially. Oh, it has 2. Okay, yeah. So then, yeah. So those solutions typically give you very high speed, but as far as I've understood, they give you then lower point cloud precision and quality. And I think it essentially the simplest explanation is just down to the amount, like the signal to noise ratio you get by doing it that way. So. Yes. Yeah, so the question is, are we using any linter like MyPy for the Python problem? And yes, we are doing that. And we have used, I think it's MyPy to generate types for Halide, which has helped a lot. And yeah, we are progressing on the path there to find the best tool. In my experience, Pyrite has been a bit better at providing more information about errors in the code. So yeah, we are looking into that currently, but there's a lot of potential, and it's in our case more about how much time we actually have to prioritize that over the other work that we do. So, but we are improving. Yes. Yes. So the question is, if you're using the C++ bindings, can you then still do the realizations essentially at runtime and not just compile it down to binary code? And the answer is yes. So Halide can essentially be run in these two modes, both in Python and in C++. So you have the just-in-time compilation mode, where it's leveraging, I think it's LLVM at runtime to generate the just-in-time compiled code and then run it. And the downside of doing that is essentially that it takes longer when you're doing it, because you have to have the compilation step. And that if you were to do that in your production code, you would essentially have to bundle the full version of Halide with LLVM included with your executable, which can become quite big. But if you do the ahead of time compiled version of Halide, then Halide provides a very small and minimal runtime that you link to your code. So for production codes, the ahead of time compiled version is definitely recommended from our side. But it's doable, and you can get pretty far with that as well. So I would say for a new project where you're just trying to use out Halide, go for it. If you're not concerned about the performance right now, then do that, and then you just know that you can ahead of time compile it later and then get the additional speed up by not compiling. Any other questions? If not, I'll be around in the lobby. Thank you all for coming.